I think that we can start. Actually, I expected very few people today at lesson, but actually the class is empty. So I came in the class and then I'm alone. So it's just okay. Like there's one guy. Like, lezione tutta tua. Lezione tutta tua. Lesson 1-to-1. Okay, so let me do this. Okay, so basically today we start with like today we start talking about convolutional neural networks that you actually already see in during the theoretical lessons with Professor Matteucci. And today we are going to see how to implement a convolutional neural network and to, in particular, apply it to a classification task. Next time we will see also how to develop convolutional neural network for example, autoencoding, and if you will have time for image segmentation. Actually, I think that if we have not time, I prefer to show you how to perform image segmentation rather than autoencoding. So see you next time. Okay. Before we start, I want to show you another way to create a data set. In particular, in the case, we are going to use an image-based task. So last time we saw that we have different ways to account for overfitting. So as we see, we have, for example, dropout layer, or we can add weight decay to our optimization, and we can perform, for example, early stopping through a callback. But another way to improve our performance, especially when dealing with images, is to augment our data. This is very useful to increase the number of, for example, to increase the number of sample if we have a very small data set, and to increase the variance of our data, so to avoid to overfit. It's just another way to prevent overfitting and to increase our data, and we can do it with a particular class exposed by Keras, which is under the preprocessing image module, which is the image data generator. So what we are going to see is how we can implement that augmentation and how we can attach our data augmentation pipeline to our dataset.
Professor, could you start recording, please?
Sorry? Okay, sorry. I just forget to. Thank you very much. Yeah, my difficulty, the challenge today is to check the chat. So I'm going to check what you're writing in the chat later. So if someone of you guys, if you can inspect the chat and then raise an hand if there is some kind of problem. Okay, I think that is recording. Yes. Okay, so as I was saying, for the recording, today we are going to see how to perform data augmentation, especially in the case of image data. And we are going to perform data augmentation in combined with a different way to develop a data loader, which is in some way different from what we have seen so far. So, as was saying, the data augmentation pipeline is we can implement our data augmentation pipeline in Keras through the image data generator class, which is a class under the preprocessing image modules, and it allows to some way to declare our transformation. So it will take an input, which is in this case the image, and then it performs some combination of transformation randomly to our data, and finally it returns the augmented images. So this is the class. As we can see, we can set a lot of parameters. For example, we can, we can rotate the image, so we can define a rotation range. So we can say to our image data generator that we want to rotate our image into a range. I don't know, for example, by passing a list between 0 and 90 degrees, and he will rotate randomly by sampling a random degree from 0 to 90. Or we can shift the image. Here we have an example on the bottom left of the image of the slide. We can shift random on the width or on the height. There is not an example of the height shift, but we shift the image on the row, and we can change, for example, the brightness of our image, or add some kind of noise, or in some way we can hide some parts of the image. And this is very, very useful, for example, if you want to I don't know, you want to prevent from the network from memorizing the inputs. So we can also zoom randomly the image, and so we have some kind of, for example, we can perform also a normalization by subtracting the mean from our inputs, or by normalizing by the standard deviation, and so on. So when we transform an image, we have also we can change the aspect of the image. and then going from the initial appearance of the image, and then by applying this kind of transformation, we have to perform an interpolation. So basically, we interpolate the data in the arrival grid when we perform the transformation. And here we can define also the, for example, here is nearest. So we can define the interpolation algorithm for our transformation. In this case is the nearest, but we can perform also bilinear interpolation or bicubic. Then we can also flip the image and so on, and apply some kind of preprocessing function. Here we can say to Keras to perform some kind of custom function. So, okay. So what we want is to, okay, let's imagine that you have a big data set of images and you want to perform a classification task. As we have seen last time, we perform data loading of very small data sets which were provided by Keras and were stored into NumPy arrays. Today we want to write a data loading which allows us to read from images from memory at runtime and to perform our data augmentation. So this is the case if you have a very big data set. It's very difficult to imagine to load it all in memory, so you can use this approach. And to do this, Keras is very performant and allows to automatically create a dataset of this kind based on a I don't know how to say. We have before creating the dataset with this modality, we have to prepare our dataset in a specific format, which is the format that Keras expects to build this kind of dataset. And we have our data to be structured in our directory in this way. So suppose that you have your dataset directory, and then you have your splits into the classical training and validation and test splits. And suppose you want to perform a classification task, then you I mean, we are performing training, so you know which are the classes of your problem, and then we can, for example, decide to put all the images belonging to a specific class to a subdirectory which is named with that class. So we can build a dataset in this way. So we have the training directory, and for the training directory we have the class 1 subdirectory with all the images. Then we have class 2 with all the images belonging to the class 2, and so on until for all the classes. The same, we perform this dataset preparation also for the validation and test directories. If we have a dataset which is implemented, which is structured in this way, we can, for example, okay, image data generator you have seen already. So we can use the flow from directory method from the dataset class. So we have the dataset class, and we see that we can generate dataset using from tensor slices or a range dataset or and so on. So the class dataset, we have seen that expose several methods to create different kind of datasets. In this case, if we call from directory, we create actually a flow from memory in which Keras read the images from memory, and we can attach to this pipeline for example, our data augmentation. So we have to, then the main parameter of this method is the directory, which is the parent directory of our dataset, which is the one we saw in the last slide. Oops, I rotate. Okay, which is this one. Then we have to say to Keras which is our target size. So we read the image from memory, and then the image is automatically resized to the target we decide. So in this example, for I don't know, this means that all the images have to be 256 pixels, both on the height and width. Then we have to say which kind of images we expect that are, for example, RGB. And this is very important, class mode categorical. If we structured the data set in this way, and we set the class mode to categorical, automatically Keras take the image and assign to the image the class specified to the by the subdirectory. So Keras recognize the structure of the dataset and rearrange the labels based on the directory we create. And then we have also other kind of parameter. For example, if you want to perform shuffling of our data set, or and the interpolation algorithm. So when we perform the resize of the image, we can decide which kind of algorithm we want to apply when resizing. Okay, so this is a generator, and then we can use the generator as we have seen last time, such like the generators we have already seen, and we can give to the method the generator to the method from generator, and we create the dataset object. And then we train as we did last time. Otherwise, we can use directly, for example, the generator. So if we want to skip the generator of the dataset, we can use fit generator instead of the fit method. Everything remains the same. Okay, so the task we are going to solve today is a classification task. So I kept this data set, which is the UC Merced land use dataset, which is a data set of RGB images of actually are airborne images, and they are picture of different kind of land. And in particular, we have 21 classes, from agricultural, airplane to, for example, runway, tennis court, freeway, forest, and so on. And the goal is, given an image, assign this image. So to find the model which, given an image, assign that image to the corresponding class. And we did this. We will do this with a convolutional neural network. So before going to the model, let's start to create our dataset. Let me share with you the link to the dataset. I'm going to use Colab. So I will give you the sharing link of the Google Drive. of the zip on the Google Drive. If you're using Colab, I'm going to show you how um, to use the dataset directly from the Colab notebook. If you are using um, your uh, your local, if you're using Jupyter in local, you can download the dataset and then you can unzip the dataset in your folder and use it the same way. Okay, so very slow. Okay, I'm going to pass the link to the file in the chat. Okay, this is uh, the link to the dataset. You can, if you are using Drive with Colab, you have to put the zip on your main Drive page, in your main Drive directory. If you're using your local machine, you can download it and unzip the file. Can you uh, tell me if you are able to admit person to the room? Can you tell me if you are able to download the zip? Okay. For the one using Drive, are you able to see the file in Drive? I think yes. Okay. Yes. Can I remove the beeps? Okay, disable. But okay, let's open our Colab notebook. I'm going to share the screen. Moment. Very slow. So, share. Sharing. Okay. Can you see the notebook? Yes. Okay. So, um, okay, let's start by importing TensorFlow. I tried to go slower than the other lessons, so if you want to follow me. You're welcome. So let's import some libraries that could be useful. For example, OS, then TensorFlow and NumPy. Then in this case are not so it's not necessary, but just for exercise, remember to set your random seeds. And then I get my working there. Okay. For the one that are using Drive from Colab, let's mount the Drive directory as we did last time. So from Google Colab import Drive, and then Drive mount content Drive. Then you have to put your authorization link. Okay. Mounted, and then we can unzip our file in the current working directory of Colab. Or actually, if you are using your local machine, you have not to perform this task. You can unzip not from code, actually. So I can access the file in Drive, my Drive, and then the name is cmesed land use.zip. Okay, unzipping. Okay, I'm waiting for you to unzip the dataset. Then we can access the dataset. I mean, if we list the content of our parent directory in Colab, we see that we have the directory. So we can access the dataset from actually from content. You see, very long. Okay, and then we have our training, validation, and test. And if we inspect, for example, the training, we have all the classes, and for each class we have all the images belonging to the class. So let's see, for example, agricultural. So, and then we have all the images that are in TIFF format.
Sorry, do you mind showing again the unzip code, please?
Sorry, I don't get the question. Can you write it, because the sound is not so good. I understood the. Can you show?
If you could show the code for unzipping.
Okay. We are unzipping we are unzipping the file which is in Drive, okay, and we unzip it in the parent directory of Colab, which is our current working directory, which is the content one. So then if you inspect the content of the content directory, sorry for the repetition, you will see the unzipped dataset folder. Okay, can you explain again how to load the dataset on Jupyter? This is for Colab. If you are using Jupyter, you have not to perform these steps because you will access directly the dataset from your local folders later when we need the dataset. So wait and you will see. But for now, if you are the important thing is that you have to unzip your file. Even if you are using your local machine, you have to unzip the file on your local folder. So, okay, let's start with the image data generator. So let's importing from TensorFlow dot keras preprocessing image data generator. And then, I don't know, I imagine that when you run your experiment, if applying data augmentation, you can see it as one of your hyperparameters, like performing weight decay or performing introducing dropout in your network and so on. So this could be parameterized. In this case, I use a Boolean, but you will have your config file when you decide how to run your experiment. So if apply data augmentation, let's create our train data generator, which is an image data generator. So image data generator, and let's decide which will be our transformation. I don't know. Let's play a little bit. So for example, let's introduce a rotation range. If I write an int, it will rotate the image from minus 10 degrees and 10 degrees. So if you don't say to Keras which is the range, it will automatically range from minus the integer plus the integer. Okay, then shift. Same reasoning is also for the other transformation. So in this case, we shift the image on the width, so on the column of 10 columns on the right or on the left, because we are shifting from minus 10 to plus 10. Same for the height. I don't know, we can introduce, for example, zoom. So in this case, we are zooming by the 30% of the image. We can flip randomly the image horizontally or vertically. I mean, you can change it just to play a little bit with the parameter. And okay, fill mode constant. Why I need a fill mode? If you imagine, for example, for a transformation, I don't know, a rotation or a shifting, when we shift or rotate the image, we introduce new pixels which do not belong to the original image, and we have to decide which is the value of that pixels. One of the ways is to fill that pixel with a constant value. So we set the fill mode as constant, and then we define the value of the constant, for example, with zeros. So when we rotate the image and we introduce new pixels, that pixels will be 0. And for example, we can perform such kind of rescaling, or suppose that we want to normalize our images, we can set the rescale parameter, which is a value that is multiplied for our images. So since the RGB values are going from 0 to 255, we can divide by, we can multiply by 1 to 255. Okay. I don't know. This is all. If we do not perform that augmentation, we can generate, for example, our image data generator with no transformation except for the rescaling, for example. The same for the valid data generator, but we do not want to perform data augmentation for validation. I mean, in this case, you can also perform that augmentation during validation, but you have to be sure that each epoch you are performing the same augmentation. Typically, is not this the case. This is not the case. That augmentation is used basically during training. So in this case, I apply only the rescaling, and the same for the test set. Okay, that's all. We have our data generator, which will perform data augmentation for us. And from now on, we can generate our data set as we did last time. No, sorry, we are going to perform from directory data set. So suppose that let's set the variable of our dataset directory, which for the one using Colab is current working directory, simmerset land use. For the one, and this is the case for the guy that asked before how to load the data in Jupyter. Here you have, if you're using Jupyter on your local machine, you have to set your local folder to the dataset in dataset dir. Okay, then we have to define the directory of each subset. So for the training, validation, and test set, for example, we can set a variable training dir, which is in dataset dir training. Then we have our validation dir, which is validation, under validation, and test dir, which is test. Okay, so now let's create the generator, which are flow from directory generators. So we are opening a reading flow from memory. So Keras will load the images during the training, and then will apply the documentation as well. So let's go from train data gen flow from directory, and we have to give for each subset. We are going to create a flow from directory dataset for each subset. So we set the training dir. We define which is the batch size, because this dataset will automatically group our image into batches. So let's define, for example, a parameter which is yes, I don't know, 8 batch size, and then we have to define the class mode, which is categorical. If you want to shuffle the dataset, yes, and the seed to perform that augmentation in a reproducible way. Okay, the same for all the other datasets. So you can copy paste this one, valid gen, and then you can simply overwrite your training with validation, sorry. And the same for the test. Okay. Let's see our the output from this method. How we can see automatically Keras detect which is the structure of our data set. And here we say that for training, he found this number of images belonging to 21 classes. So it finds that the dataset contains 21 classes, and as well the same for the validation and test set. So in this specific case, we have the same number of images for validation and test. Okay, so at this point, we can create, for example, our train dataset by calling TensorFlow.data.dataset from generator. This is the same as the other times. So we have to give the callable generator. Then we have to define the types in output. So we have float 32 bits, and also the labels are floating point, and the shapes. The shapes are a list. Batch size is none, so we have a dynamic batch size, but we have to define our image size, which is 256 pixel, and by 250 pixel on the width. So we have 256 rows and 256 columns, and 3 channels because we have RGB images. Targets instead will be batch size, number of classes, where number of classes are 21. I'm going to copy paste this for all the subsets. Okay, so valid. Valid. Test. Test. Okay. And then we do not have to forget the repeat. So train dataset equal to train dataset dot repeat. Otherwise, the training will stop after the first epoch. Oops. Yeah, sorry, equal. Equal. No, that number does not include the augmentations. That number is the number of the original images. Then you at each epoch you will have the same number of images, but they will be augmented. But the number of images do not change. Okay, so I don't know. Let's test our no. Let's test our data set. For example, let's plot our images from matplotlib. So let's import pyplot from matplotlib. Then for the one using Colab, I found that you have to use this magic. Otherwise, it will give problems in visualizing the pyplots. For the one using Jupyter, you will not have this problem. Instead, maybe you can use also the notebook that allows to visualize better in Jupyter. So let's define, for example, one of the method to iterate on our data set is to wrap the data set into an iterator. Let's create an iterator, and then, for example, in another cell, let's let's get the augmented image and the corresponding target by calling next on the iterator. Okay, this is a batch of images, so let's take only the first and convert it to an array because it is a tensor. Okay, so then denormalize the image. By multiplying for 255. And then we can call imshow of the image, which has to be casted to an unsigned integer 8-bit. And finally, let's plot. Okay, I'm going to wait until you are able to reach the same point. So if we continuously call the cell, we are calling the next element and plot on the screen. So let's have fun. And as you can see, the images are augmented, are shifted and rotated, or zoomed, like in this case. And they are also combined. You can have randomly multiple transformation combined, so you can have zooming and shifting in the same at the same time. Okay, and so on. So we have our working data set. Can you please show the previous cell? Which one? This? Okay, I'm going to wait. Okay. So we have our data set. Let's implement our training and our model. In particular, today we are going to use a convolutional neural network, which takes the name from the layers which compose it, that are convolutional layer, which take the name from the convolutional operator. So who wants to remind what is a convolution? Do you remember? If I'm on notebook, I have to skip the cell import. No, if you are on Jupyter, you can skip the matplotlib inline, but the library, you have to import it. Okay, so what is a convolution?
Basically, we apply a linear filter over the pixels of the image, but usually the filter is smaller than the image. So for each resulting pixel, we aggregate a linear combination of some pixels of the image in a confined area.
Yes, exactly. So it's a linear transformation. I don't know if I'm going to write on the blackboard. If you will see, I try to write it as bigger as possible. So let's perform an example. For example, for a 1D data. I'm going to write it very big because I don't know. Yes, you are going to see it very small. Okay. So this is the value of our 1D data. And for example, suppose to have our weights, or commonly called kernel, which is composed by 3 values. Okay. The convolution operation is simply sliding this kernel and perform the weighted sum of the values of our input based on the weights of our kernel, on the values. So for example, we are going to apply our kernel to the first 3, then we shift the kernel and apply the kernel to the second 3, to the second group of 3 elements. and so on. And then the results, for example, here is the value times the first value of the kernel plus the second value of the input times the second value of the kernel plus the third value of the input times the third value of the weight, and so on. So the parameter is shared among the position, and this allows to significantly reduce the dimension of our network. So and to optimize also the to obtain faster operation and to optimize the memory consumption, and also to perform a combination of sparse operation, and to apply the same kernel. For example, if you imagine an image, this process allows me to apply a kernel to the different parts of the image, and this allows to learn specific filters which locally are activated by some kind of pattern. So if you imagine that a filter activates for some kind of edges, there is no reason to that the filter will not activate for the same edge in other parts of the image. So this is very useful. And okay, if you have our volume, which is, for example, the feature map of our network, we are going to apply a kernel, which is not a 2D kernel, but it is a volume as well, which has an height, a width, and the number, the depth of our kernel is actually equal to the number of channels in input. So let's call it the same way. So the shape, the dimension of our kernel in a convolutional layer is defined in this way. And the operation performed is to slide this volume over the image. The step you shift the kernel is called stride. So also in this case, we can define the stride. And then by shifting the kernel across the image or across the volume and summing all the values under the kernel, we obtain a one-channel feature map, where this point is given by the weighted sum of this volume. Then, if we use n filters, okay, this is filter 1, better, kernel 1, then kernel n, we obtain n feature maps. Then, for a convolutional layer, the number of output, the number of total parameters for a convolutional layer is h times times width of the kernel times the number of input channels times the number of output channels. This is the total number of parameters which we will have in our convolutional layer. If you want to apply a feed-forward neural network, not convolutional, to the same input, you will have a parameter for all the points in input, and you will discover that they exponentially grows. So this is allows to contain the number of parameters. So let me come back to the implementation. Actually, let me go to the slide. Okay. So in Keras, what I described here is implemented with the conv2d layer. So we have to define the filters, which is the number of filters, where the number of filters you can see it how to define the number of output channels. So actually, the number of output channels equals to the number of filters, n. Then we define the kernel size. The kernel size you define is the 2D one. So you define which is the height and the width of your kernel. You do not specify this dimension because this comes naturally from the input. Because we are performing 2D convolution. If you are performing, for example, 3D convolution, then you can set also the number of channels of your kernel, and then you slide the kernel also on the depth. But this is the case. Okay, then you can set the padding. So, sorry, before the stride. So which is the step of your kernel shifting, which can be different for the rows and the columns. Typically is the same. And then the padding. The padding can be basically of two types, valid or same. Which is the meaning of padding? Okay, suppose you, maybe I have a slide. So this is just what I tell you at the Blackboard. Then the strides. Okay, the padding, it's useful when, for example, we want the input to be fully covered by the kernel. Because if you have, for example, I don't know, 4 by 4 input, and you apply 3 by 3 kernel, you will have, and for example, stride 1, you will have, you apply the kernel first in this position, and you get your first value. Then you shift by 1 and apply the kernel on this position, and you get the second value. Then you shift on the second row, and you get this value. And then you shift and get this one. As you can see, your dimension is changed. So convolution changed the dimension, or your spatial dimension. If we want to preserve the input dimension, we can set the padding to same, and then a padding of zeros is applied to the input, such that applying the kernel with stride 1 gives an output with the same dimension. Because if here you imagine zeros, I apply the kernel here, then here, then here, then here, and I obtain the same number of points as output. With the valid one, with the valid value, we are not performing padding. So we'll have a different output for stride 1. Okay, then there are other, basically the other parameters are the same of the dense layer. So we have the activation. Once we get the output of our convolution, obviously we eventually sum the bias, and then we apply the activation function. And here we can define which is the activation, and then the initialization, for example, for the kernel, or for the bias, or the regularizer, and so on. So this is an example, very old, of a classification of a convolutional neural network for classification. So typically, we have a convolutional neural network made by convolutional layers. We extract some kind of features, which are actually volumes. Then we flattened. We flat the volume into a vector format, and then we apply our classifier, which is a dense layer with C number of output neurons, where C is the number of classes. This is the typical configuration for a convolutional classification network. And typically, this part, as you have seen at lesson, is made of blocks. Each block compute a convolution, perform the apply the activation function, and then perform the max pooling to reduce the number of parameters and to basically to reduce the number, the spatial dimension of our volume. So each block is conv plus activation plus pooling, where pooling can be of different types. The typical pooling is the max pooling, when we get the max under, it is like applying a convolution, but every time we shift the filter, we take the maximum under the filter position. Okay, let's try to write it down. Okay, so we can use a sequential as well. So let's suppose we define, we are going to, we are going to, yes. Ah, sorry. Thank you. Okay, we are going to write the convolutional neural network recursively, in the sense that in a for loop, we create the single block, and then we stack the block one after the other. And each time we start with a number of features. And so, for example, number of features starting, sorry, with this. And each time we go to the next block, we increase the number of features of 2 times. So here we have 4 number of features and then 8 number of features. As you have seen probably during lessons, this is typically done because if you are reasoning about it, when we are extracting the features at the first level, they are typical very low level features. So very low level of abstraction. Typically you are recognizing colors or edges and so on. And the number of features you can learn, the number of useful features you can learn here is typically low. While as we go deeper to the network, we increase the receptive field and we get increasing level of abstraction. And our abstract representation could be very large. So we increase the number of features as we go deeper to the network. So let me set the variable with the starting features, and I define the depth of my feature extractor. So I define how many encoding blocks I will have here. Then I define my sequential. And then I start in cycling on the depth. Okay, if I am at the first layer, I have to define the input shape for the same reason of the last times. The first layer have to have the input shape to be specified if we want to inspect the final dimensions on the summary. So if I am on the first layer, I define the input shape as a list. So my input is the image dimension, so with 3 channels. Otherwise, we can left it unknown. Then I'm going to add the first layer of my block, which is a com2d, where I define the number of output filters, which is start f. Then I define the kernel size. For example, let's apply a 3 by 3 kernel. Then the stride, I want the kernel to be shifted of 1 position at a time. I want this convolutional layer to not change my input dimension, so I use the same padding, and then I define the input shape, which will be set only for the first one. Then I'm going to add the activation layer, for example, a rectified linear unit. And finally, I use, for example, max pooling, which is max pool to the layer. And I'm going to define which is the kernel of the max pooling with pool size. I don't know what I'm looking. Okay. Which is 2 by 2, for example. In this case, I am halving the input dimension. Probably 1, 2, 3. Okay. And then, since I'm cycling, finally I multiply by 2 the starting features. All these is just this part. So here I have a feature, the feature extractor. Then once I obtain my features, my final features, I'm going to apply the flattened layer. So I'm vectorizing the volume. And finally, I apply a classifier. So I don't know, a dense layer, for example, with an intermediate hidden layer of 512 neurons. Also, in this case, I'm going to define the activation. In this case, I'm defining the activation directly in the dense layer, just to change the things a little bit. And finally, I have the output layer, which performs my classification as well, just like the our last examples. So number of units equal to the number of classes, and activation softmax. Yes, sorry. Thank you. Okay. I'm going to wait a minute for you to complete the model. So that's solving the data scarcity problem. Actually, each epoch you are continuously transforming your input data, so you never see the same data each epoch, and this allows to increase the variance of your data set, and because you are theoretically generating an infinite number of images. This is obviously limited because also if you perform data augmentation, the images are very similar to the original one, but this helps a lot during training, especially if you have a small data set, and you are probably overfitting a lot. Why we repeat this for each level of depth? Because the typical structure of an encoding, convolutional encoding, is convolution, activation, pooling, Then you stack another convolutional block, which is made by convolution, activation, pooling, and so on. And this is the depth of my model, of my feature extractor. Simply in the code, I'm dividing these, and with a single cycle, I create all these layers. And the number of output features from the convolution is set to be 2 times the number of features in the previous layer. Number minus 1, and so on. Okay? So in the code, the start f is the first of the series to compute the others. Okay. So are variables correct? I think yes, because otherwise it will give me an error. Yes. Okay, so we have our model. Then let's try to inspect the model. Okay. So here we have the shape. As you can see, after each block, thanks to the padding and to the pool with kernel 2 by 2 and stride 2, we halve the dimension, the spatial dimension after each block. So we start with 256, and then we go to 128, and so on, until at the end of our convolution, we end up with 8 by 8 spatial dimension, and we have finally 128 feature maps. So this is the features that will be then used by the classifier. And okay, on the right, you will see the number of parameters. For example, the first layer, for the first convolution, we have 224 parameters because we have 3 times 3 the spatial kernel size, and we have 3 channels in input because we have the very first input is the input RGB times the number of filters, which are 8. Obviously, plus the biases, which are equal to the number of filters, gives 224. Okay, so we are ready to train our network. So as usual, I'm going to define which is the loss, except for the feature extractor, nothing changes. I mean, it's just how we extract the features. From this point on, we are going to use the same code. So we compile the model, We use categorical cross entropy as well. We apply the optimization algorithm as usual. So the part we changed is this one. And okay, and this is the innovation of deep learning. This part. Before this, the features were handcrafted. So here we have the human who extracted the specialist who extracted the feature. Now we are going to learning from the input to the output automatically. Okay. So categorical cross entropy, learning rate. I don't know. I did some tests, and this is a good learning rate for this problem. Optimizer. Let's use Adam. And finally, we can plot, for example, the accuracy. And then we call compile optimizer equal optimizer loss equal loss and metrics equal to metrics. Optimizer. Okay. Then for the one using Colab, let's open TensorBoard. And define your log dir. I created a folder in Drive which is called keras3. So you can save your log wherever you want. Classification experiments. Okay, I'm opening TensorBoard now because if I start the model fitting, then I can see TensorFlow updating at runtime on Colab. If you're using your local machine, you can you can apply your model fitting, run your model fitting, and then you open TensorBoard from terminal. Okay, I have already some experiments. Okay, actually, this part is identical to the one of the last time. So if you have your model, if you have your notebook, you can copy paste that part, which is the part in which we generate the directories for the TensorBoard and checkpoints and so on. So let me open my I'm going to copy paste. If you want, I can copy paste it to the chat. So it's the same. For everyone. I don't know if no, it will format it very bad. So maybe it's better if you can copy from your notebook. Simply, it's the one of the last time. Simply change the new folder. I call it keras3. You have to create the folder in Drive if you're using Drive. Otherwise, I mean, the folder name is the one you want, the one you prefer. I simply change this part because I have memory problems and I don't want the checkpoint to be saved at each epoch, so I overwrite the checkpoint each time. The rest is the same, and I activate the stopping. So I'm going to give you a minute, but in the meanwhile, I'm running the model fit, in which simply I'm setting the training dataset, the epoch, the max number of epochs, the steps per epoch, which is equal to the length of the train generator, the validation data, which is my valid dataset, and validation steps equal to the length of my generator. And finally, I gives all the callbacks I defined in the previous cell, which are the one of the last time. I forget to use the GPU, so it will be very slow. Okay, so, but it's the same. Okay, it is empty because it is very slow on CPU. As you can see, the things really change when we use convolutional neural networks. If we are using CPU, because we are increasing our input dimension, we are increasing the number of features at each block, and this is very this has a very bad performance on CPU. This kind of part is really optimized to go to a GPU or TPU, obviously, because perform operation on tensors or matrix operation on convolution and so on. Optimize things. So in this case, when we jump to the convolutional world, it starts to become important to use some kind of acceleration. And this is a toy data set, is something simple. If you will work on a big project with very high dimensional data, for example, like hyperspectral data or I don't know, satellite radar images, it will have the input will have, for example, 1,000 by 1,000 pixels and so. Okay, so we did the first epoch. Okay, good. Okay, let's play with the training by yourself and see if you are able to train. I started some kind of train here, for example, and here I'm starting to overfit, and then with the early stopping, it stopped at this epoch, for example, for this experiment. Okay, let's say in this last 10 minutes, some kind of useful thing you can do, which is, for example, okay, actually, I wanted you to show how to compute a confusion matrix and how to plot the confusion matrix as an image in TensorBoard. So I wanted to show you how to also save images on TensorBoard. But since we have no time, I prefer to show you how to use, for example, transfer learning. and because I think that is more important. And I left you the code, the notebook with the confusion matrix. Actually, the confusion matrix, for the one who do not know which is a matrix with number of rows and columns equal to the number of classes. Here we have the number of true classes, and on the columns the predicted one. And actually we have an it if we predicted the true class on the diagonal, and we can keep, and if we are wrong, we have values off of the diagonal. In particular, if the true value is, for example, agricultural, is the class 1, but we predict class, I don't know, class 3, here we have a false negative. If instead we do not have that that class, but we predict that class, we have a false positive. And this is very true this is very useful in a multi-class problem to inspect what is happening, because maybe we are reaching a very high accuracy because we are very good in predicting the first true classes. So here we have all the values on the diagonal, but here we are wrong. We are predicting wrong for all the other classes, and for some reason our data set is unbalanced. So we have an higher number of these two classes, then the accuracy will be high. So it is useful to inspect what happens for each class. And there is a method from scikit-learn to compute this matrix. Then we convert this metric into an image, and we can plot the image on TensorBoard. It's very there are very few line of codes, and I will put them on the notebook. Let me show you instead how to use transfer learning. Who wants to remind which is transfer learning? I don't know. Have you seen transfer learning during lesson? Okay. Who wants to say which is? No one? No one wants to say what is transfer learning? Exactly. So just to repeat, transfer learning is, okay, what if I remove this part and replace this part with a model which has been already pre-trained from someone else, for example, to a bigger data set. So looking to my data set, for example, I understand that my data sets are very similar, for example, to other data sets, or I understand that some feature that can be extracted from my data set can be the same of the feature that can be extracted from another pre-trained network. So instead of training from scratch, I can take a network which has been already trained and put that network instead of mine. This concept is transfer learning. Then here I can have what I want. There are different models that are available for transfer learning. Some of them are already contained in the Keras framework. For example, the BGG 16 is one of the most used, trained on ImageNet, which is a very, very big RGB data set. And then we can import this part, put the BGG 16 Okay, the VGG16 is a model that is composed by the feature extractor. So the VGG is composed as well, as in this case, by a feature extractor and a classifier. Obviously, the classifier is trained on, if I remember, 10,000 classes. So it's not useful in this case. So I keep the feature extractor. I remove the classifier from VGG, and I take my classifier and I replace the classifier with mine. So you can see it in the other way. So I keep this and I replace this with my classifier, or I keep this and replace the feature extractor with VGG. Okay, we have no time to write it, but I can show you. Let me. So let me run this cell that are the same. I hope that I have not, no, again. Zip. Sorry, I have to perform again all this stuff. Okay, so for example, we can get retrained models under the Keras application module, and followed by the number of the model. So check the application module to see the list of available models. We can say which weights, how the pretrained model is initialized. So in this case, we are saying to Keras that we want the weights of the model trained on ImageNet. There are also other possibilities, I think, but ImageNet is the most used. Include top is equal to false, because I'm cutting off the classifier. If it is true, I'm going to the return is also is the complete model with the classifier included. And I define the input shape, which is the mine. Okay, then here, for example, okay, here we are downloading the model. Let's have a look. So this is VGG. Then, okay, in this code, I'm doing, I have I have a fine tuning parameter, because in some cases, typically, basically in transfer learning, we are replacing the feature extractor. Then we fix, so we are not training these weights anymore, but we are training only the classifier. So this is fixed. We are not updating these parameters during backpropagation. But in some cases, especially when my data set is very different, contains images that are very different, for example, from the one that are contained in ImageNet, as we increase the level of abstraction, so as we go deeper, the features have to be very specific for my problem. So my problem is classify land usage in this case. If my pre-trained data, my pre-trained model comes from a pre-training from, I don't know, cats and dogs data set, is not very useful. But it's useful, for example, for the first layer, because the first layer I know that are low-level features. So are features like, I don't know, edge detection, color detection. So I can say, okay, instead of training from scratch, it could be very useful to have this feature already extracted from the pre-trained model, but I want this feature to adapt to my actual problem, which is classifying land usage. So I started from the weights of the pre-trained model, which is, however, a better initialization than random, but I am also learning these parameters. So if fine-tuning is true, okay, if I want to fine-tune, that means I start from the pre-trained weights and I'm fine-tuning, I am adapting them to my problem. I set these weights to be trainable. So I have a freeze until. Freeze until means that I want, starting from the first layer to some point, I want the pre-trained model to be fixed, and then I want to adapt from freeze until on. So freeze until is, for example, the first 15 layers. So I keep fixed the 15 layers. I don't know which are in this case. We can simply count the number. I mean that I take all. I think that I'm taking all the encoding blocks, and from this point to the beginning, I'm setting the variables to. I'm setting the trainables of this layer to false. That means when doing gradient descent, do not update this part. So this part is fixed. But these are trainable equals to 2. If I don't want to fine tuning, I put all this stuff to be not trainable, so is fixed, all the feature extract. And then, okay, from the sequential on is simply my classifier. From this part does not change. It's exactly as before. And then I can train my model as well. Okay. I have no more time. So if there are questions, I have just a few minutes to change the room. It's all clear? Is it clear? Okay. Before I'm very last thing, important actually, this part. Obviously, my pre-trained model, like VGG, is trained in a specific way. So, for example, images can be normalized in a particular way. So if we want to the features, if we want the model to work as we expect, actually we have to reproduce. It's not necessary, but it is better to do it. We have to reproduce the same normalization as the one used in the pre-trained model. How we can do it? We can use. Do you remember the preprocessing function we cited at the beginning of the lesson? we can set with a function that comes from the VGG16 applications. So from chaos application VGG16 import preprocess input. This one, so each model exposes a function, offers a function which allows to normalize the image as expected by that model. And then we give this function to the preprocessing function parameter of the image data generator. So we perform our data augmentation, and then we apply normalization as provided by the pre-trained model. We did it very fast in transfer learning, but actually is not so complicated. We have to import the model, and instead of writing our feature extractor, we have to import an already model until a certain point, and then we train our classifier. Okay, just before closing the lesson, just a communication. We decide that it is better for the projects if the groups are at least of 2 persons. So we prefer if you can create groups of 2 persons. So let's try to find someone else to perform the project with. Okay. If there are problems, write to us, and then we can see how to fix. Maybe the one that remains alone at the end, we can couple them as well. Okay. If there are no more questions, and at most, I think that we said three people. I don't remember what the professor said. I think 3. Does using that augmentation is always a good option? No, is a good option if you are overfitting, if you have a small data set. Otherwise, if you have enough data, you can avoid to use the augmentation. Okay, thank you. I have to switch class. If someone wants to repeat the lesson, see you in 15 minutes. Okay, let me stop recording. Okay, then I have to close.